Welcome everyone to lecture 13, computer vision course. So today we'll be talking about transfer learning, pre-trained models, the need to do transfer learning, and how useful it can be for new data sets. So here's some references, generic references. Specifically, we'll be looking at this reference and this reference for our lecture today. And some other references that we've looked at in the past, ResNet, GoogleNet, more publication related references here. Okay, so the last couple of lectures, we've been looking at introduction to the CNN architecture. We've looked at comparison to neural networks and how CNNs are fundamentally different or specialized formats of generic neural network, especially the use of convolution and max pooling and other modules like inception module or the ResNet module, for example. And we also looked at the evolution of the CNN architectures over the years, actually over the past decade, to be precise, like 2012 and this 2022. So 10 years of evolution and improvement in accuracy across the board. And like ImageNet is one data set. If you think about it, the benchmark has been ImageNet, but it's also one of the largest image data sets. It has thousands. Even though the benchmark has been one data set, because of the diversity in the number of classes of the image data set and of the extent of the ImageNet, it's so huge. It has like a million data points. Because it's so huge, if you're making improvements on ImageNet, it's very likely you'll be making improvements on other image data sets as well. So benchmarking on ImageNet is very much justified because of the scale of ImageNet. So the past decade has seen an evolution of CNN architectures from AlexNet all the way to the more recent ones that we saw as well. And we also looked at deep dive into performance, trade-offs, quirks in training CNNs. We saw there were some quirks, for example, with ResNets. There was a quirk that you could increase the number of layers, but then you would fall into an optimization issue, a degradation of performance, and that's a quirk of deep nets, which was resolved through ResNet. So there is quirks, and I would also say there is like hacks. So there's like hacks in deep nets that if you use these hacks, usually you do well. So a lot of these hacks are also inbuilt into, let's say, a Pytorch module. They're really like the default parameters are already optimized so that these hacks are used. For instance, learning rate or learning rate schedule. These are things that people have already tried and tested for deep learning in general, and they also apply to CNN models, right? So you don't have to retrain or calibrate these hyperparameters from scratch. And we also looked at specific architectures, like we looked at LayNet, we looked at CFNet, we looked at AlexNet, we looked at VGGNet, Inception, and ResNet. So that's quite a variety, and also it has an evolution between one to the other. And I would encourage you to try any or many of them for this mini project, because you have the ability to just fine tune or use a pre-trained model like we'll discuss today. So you can just replace one with the other and see how the performance changes, and you can just get to know these architectures even better, and you'll know them better when you actually use them or train them in Pytorch, right? So definitely feel free to use this as an opportunity to not just try one net, but multiple nets, and see which ones are giving you performance. And really, okay, I use ZFNet and I use Inception. What's the gap? So see for yourself what the gap in performance is, and maybe there is not as much gap on the fashion MNest. And why is that so? Like, ask these questions if you see these kind of observations. because ImageNet is such a big data set, so you might expect bigger gaps in performances. But with smaller data sets, maybe a simpler net is also good enough to differentiate between the classes. So those are some things to understand as you experiment with this in the mini project. Okay, so today we'll focus on transfer learning in CNN, aka how to not reinvent the wheel with CNN training, right? And also we'll kind of do a rundown on a Pytorch tutorial on transfer learning. So there's many tutorials available already on the web, which you can just import and start experimenting with very quickly, and you get results very quickly. Especially on a smaller data set, there's not much training time or retrain time, so you don't have to spend days worth of effort in training a CNN model. So transfer learning. How many of us have heard of this before? The term transfer learning. Okay, see one. Okay, one hand. Okay, so the idea of transfer learning is what it says. A model that's trained on one domain or one data set can perhaps transfer. What are you transferring? You're transferring the learning. You transfer the learning to another domain or data set. And we as humans also do transfer learning all the time, right? You see an image of a car in daylight and you can recognize it in nighttime, right? It's like, yeah, that looks like a car. Or you see a new object and you can recognize it in different settings. So you're able to transfer context. And you can think of other examples where we humans do transfer learning all the time. You switch a context and you're like, oh, the context is different, and so this is what it means. Or interpreting sentences, that's another example. A sentence has a context, and when you change the context, you are able to transfer what it means in that new context. So transfer learning is not something very new, but it is very useful in training models, especially when you have something to transfer. For instance, with images, you want to transfer features, right? How do you train a model on images? Well, you need features to begin with. What if you already obtained features from some other model? Why not use it or transfer it to your new model and not have to do it all from scratch, right? So that's an example where you would want to transfer. And also with big CNN architectures like Inception, okay, I have like 30 layers, or ResNet, maybe I have 50 layers. Sure, you have the whole network, but training from scratch is cumbersome and it's a wasted resource. Someone spent days training, optimizing, hyperparameter tuning these big architectures, and it's available. You can just go look at saved model parameters and you can find exactly the model parameters that led to this accuracy. Why would you want to redo that from scratch if you can use parts of it for your new data set? Of course, it's a new data set, so you cannot expect the best performance with a pre-trained model, but maybe you can use parts of the pre-trained model and then add in your own new layers that you want to train or tune your model on, and then you get the best of both worlds. You use your new data set, but you don't have to retrain from scratch such a big model. So that's the whole idea of transfer learning in terms of CNN architectures. So we use pre-trained models. So any of these, you can say VGG, Inception. Someone has trained it, optimized it. It's pre-trained. It's already trained, but on a different data set. It's not trained on your data set, but it's trained somewhere. So that's pre-trained. But you may want to fine-tune it because it's not specialized, right? So any of these pre-trained models, they have a generic component and there's a specialized component, right? So you want to keep the generic component and you want to kind of fine tune or retrain the specialized component. If you saw our description of CNN architecture from a past lecture, we said that you have so many layers, but the first 80% of the layers is just feature extraction. And the last 3 or 4 layers corresponds to classification. So that 80% is your generic feature extraction. So we don't have to retrain that part. So usually people freeze that portion, and then the last layer or two, or where you're doing the classification, right? That's where you want to retrain or fine tune. So that's the whole idea of transfer learning. So the generic component gets transferred. So this is usually features learn. So you get transferred to your new model. But the specialized component, which is the specific task you have, it could be classification, it could be other things. It could be object detection, or it could be image to text. So we'll be looking at image to text models, image captioning. Those are the specialized components because that's your task specific thing. That is something you want to fine tune or train from scratch. Okay. So that's a whole area of transfer learning, but obviously there is many ways to do transfer learning, and we'll discuss the different ways. We'll discuss the pros and cons. We'll look at which strategy for transfer learning is suitable for which setting. Okay, so we'll look into that. And yeah, you get a better starting point. Even if you're fine-tuning some of the layers of CNN model, so let's say you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then maybe you kind of freeze these, and then let's say you're fine-tuning these. So even if you're fine-tuning these, you can have starting points from the pre-trained model and then fine-tune on your data set. Or if you're, let's say I'm also using these 2 layers, I can again start from, I don't have to start from a random initialization. So any of these parameters, like we discussed for stochastic gradient descent, which is the underlying optimizer for neural networks, requires a starting point. And what's the usual starting point? Like we discussed this before. Anyone wants to just quickly put on the chat, what's the starting point for parameters? If I didn't have any starting point, what would I use? Random, right? Like I have no idea what my parameters should be for my optimal model. I start random. So random starting point is a starting point, but if you already have a pre-trained model, the pre-trained model's weights or parameters could be your new starting point for the layers you do want to fine tune or train. Okay. So they may not be optimal, but they could be a good starting point because they were again trained on images. So they may have been trained on different images from the images that you care about for your data set. For example, Fashion MNIST, that's the data set for mini project that connects to fashion images, whereas ImageNet might have even images of animals or other classes that are not pertinent to image Fashion MNIST. But you can still start from there and then fine tune. Okay, so you don't have to start with a random starting point. So yeah, you get a better starting point. You save train time because, hey, I've frozen all these layers. So I am not retraining any of these parameters. So I save time, and then, yeah, so you get better results. So here's how, training from scratch versus transfer learning looks like. In the top scenario, you might have, like, let's say we looked at some of these models, you might have 4 million parameters, and then these are trained from scratch. So each of these 4 million parameters, you initialize randomly, some random float, and then you start doing stochastic gradient descent. You're using all of this data, and then you know what the classes should be. You direct the model using a loss function, optimize it, And then hopefully at the end of it, you get 4 million new parameters that are optimized at a local minima for this loss function that can do good predictions on the classes that you care about. So that's training from scratch, and that's what we discussed earlier. Transfer learning, what we do is we take a pre-trained CNN model, and then you might get some output out of this, and then you only fine-tune your network weights on the new task, and these might just be one or 2 or 3 layers. It may not be too many layers. You can even just do one layer. But this one, you don't do anything. You just use it as it is. So that's the gist of transfer learning. There's a few nuances here, and we'll talk about the nuances as well today. So yeah, so instead of 4 million parameters, you might still have many parameters. Why is that? Why would you still have many parameters even though I've frozen most of the layers of CNN? Any thoughts? Let's say I have like a 30-layer inception model. I've frozen 27 of the layers. I'm not going to retrain them. I'm going to train the last 3 layers. I might still have a million parameters. Why? So the clue is on the kind of layer that you have, right? What kind of layers do you have at the end of a CNN model? You can maybe type in the chat. What type of a layer do we usually see at the very end of a CNN model? Yeah, so you see a fully connected layer, right? It's a dense layer. And dense layers occupy the most number of, or contribute to the most number of parameters as compared to convolution layers. So even though you've frozen most of the layers, you'll still have significant number of parameters unless the number of classes that you have to predict for your new task is much smaller than, let's say, an ImageNet. So even in that case, you might get away with fewer parameters, but still you might, instead of 4 million parameters, I might be having 1 million parameters here. So I might still be having a million parameters, but it's still significantly smaller. And if you have even fewer classes, you might have even fewer parameters. And we've discussed how you do ballpark computations on the number of parameters given a CNN architecture. So hopefully you're comfortable with just looking at an architecture. Okay, I've frozen these layers. So how many parameters do I have left to train? Would I be overfitting or not? These are the kind of questions you can ask yourself and also answer, at this point, right? Yeah, so is all the parameters in pre-trained CNN fixed? This is something we will discuss. So that's a very good question. And that leads to different, models for transfer learning. So whether you fix all or not, those will lead to different kind of models. So that's a very good question. Okay, so here's another illustration of transfer learning. Let's say I trained on, color images of, let's say, different species of birds. I have all these convolution blocks and FC layers, and I make predictions. Let's say I have a new data set. So this is my new data set. And these are more of black and white images of, other maybe birds or some other species. And I want to transfer some learning from here to here. So these convolution blocks, they might still be capturing generic features of images like edges, or what kind of color blobs do you have, what kind of variations do you have in the images, where are you detecting objects. So these might be generic features that might be able to transfer from here to here. So let's maybe fine tune these, or you can even freeze some of them. So you can see frozen or not. So that's an option. You have an option to freeze, or you can train them. Usually you freeze this way, and then you can fine tune this way. So somewhere you start to fine tune, somewhere until some point you freeze, right? That's usually how it's done. And then you also have these new layers, which you can train from scratch. You can use random initialization, or you can also use initialization from here. And then the number of classes, again, might be different, right? So this is what we spoke about. Depending on the number of output classes for your new data set, that also impacts the number of parameters. That definitely impacts the number of parameters in the last layer. If you remember, the number of parameters in the last layer is the number of neurons in the layer before the last layer, and then the number times the number of labels, because it's fully connected. So if your number of labels is smaller, then you'll have fewer weights in the last layer. But then if you have many such FC layers, then again, it depends on the number of hidden neurons. You might still have more parameters showing up because you have many FC layers. Okay, so this is one example of what you're trying to transfer and what are you trying to learn from scratch. And FC layers are usually where classification starts to happen, right? All of these you can say are contributing to features, and this is where you want to classify. So even if you look at logistic regression, that's one FC layer, isn't it? If you look at the very first model that we looked at, it's one FC layer, and you had some features, image features that are supplied from somewhere. Maybe you have SIF features or some other features that you're using for logistic regression. So that's one FC layer. You can have multiple FC layers if you want to capture nonlinearity in these features. So these are my features. I obtained something. Let's say I got a 4096 vector from all of this, okay? Let's say I froze everything. I took an image, passed it through the whole convolution block, and I got a 4096 dimensional vector. That's your feature vector that you're getting out of the CNN, right? Pre-trained CNN. And then I pass that in to my FC layer, and then maybe I want to have 2 or 3, or for nonlinearity, I might want to have a few more FC layers so I can do a little bit better on performance, and then I do the classification, right? So this is kind of what we looked at before as well with neural networks. So all of these things kind of come together. You can see feature extraction, classification using neural networks, and then making predictions. Okay, so this is one example of transfer learning. Here's like more examples, and this should hopefully clarify what are we trying to transfer and what are we trying to retrain from scratch. So here's like one model for transfer learning is I do absolutely nothing. I take my, let's say, what's your favorite model? Let's say ResNet. I take a ResNet, I apply it to fashion MNIST data set, I look at the predictions, and then hopefully those predictions make sense. So, the only thing is, if you just take, let's say ResNet, that's trained on ImageNet, guess what? It's going to predict from 1,000 classes that don't even make sense for fashion MNIST. So you may not be able to do that for fashion MNIST. So the option one may not even work because you're not doing any, maybe you have to fine tune it on your new data set to how many other classes you have. Let's say, do we have 10 classes in the fashion MNIST? How many classes do we have? 10, yeah. So you may have to fine tune it to predict between the 10 classes, because only then does it even make sense to just use the pre-trained model as it is. Okay, so that's option one. Option two is usually what's done in practice and transfer learning is you freeze this part, the pre-trained convolution base, because that's giving you the features, and then you have a new classifier here. Okay, you essentially you can even think of it this way: just take a pre-trained model, throw away the last few layers, get the feature, pass in an image, get the feature vector from there. Maybe it's 4,000 dimensional or whatever. Pass that in to this new classifier model, and then that make predictions from there. And then there's the third one, which is which can also be done if you have larger data sets, is also fine tune your convolution layers. Right. So, and there are use cases for this as well, but there are also conditions or prerequisites for you to be able to go into option 3. And you can see the extreme end of option 3 is, all of this is blue, right? If the entire pre-convolution base is blue, that means you're retraining everything from scratch. Okay, so the extreme case of option 3 is retrain CNN net from scratch, which is cumbersome, which is expensive, which is what we've been trying to avoid with transfer learning. Okay, so you can see this is these are the 3 kind of paradigms for transfer learning, and typically, and also for your mini project, this would probably be the most useful, is freeze most of the layers and train on 1 or 2 of the layers. Okay, this is another illustration. You have your, let's say, your pre-trained network. You have, let's say, 1 million images. This is ImageNet. Earlier layers are learning low-level features like edges, blobs, colors, right? Later layers are task-specific. So you freeze these, and then you use the new layers to train, and then you make predictions out of that. Okay, right. So some more motivation for transfer learning. We don't have to reinvent the wheel. Earlier layers of a trained CNN net can be a starting point. A large CNN model can take a lot of effort and time to train. So it's not just training, you have to do hyperparameter tuning. Some of these models with lots of parameters can even take like a week to even train. So you don't want to spend in a lot of effort and retrain things from scratch. No need to duplicate effort. So we can reduce time by using something called CNN codes. So we'll talk about CNN codes or features from a pre-trained model. And also your context, your data set may not permit training of a full CNN model. Why is that? Any thoughts? Let's say you have a new data set. You just simply cannot do training of a full CNN model. Any thoughts? Yeah, see, notice what happens if you have less data and you have so many parameters to train from scratch. Then you're going to overfit, right? So overfitting is an issue if you have too many parameters and too few data points. So your data set, depending on the size of the data set, you simply cannot do full training of a CNN architecture, right? So these are the reasons why you probably want to do transfer learning. So we spoke about CNN code. What's a CNN code? CNN code is essentially a feature vector for an image that you obtain through a CNN architecture. So let's say this is, what is this? This is AlexNet, right? This is our 2012 ARC. So let's say you want to use AlexNet to get a feature vector. You take in an image, you input an image, you just do feed forward, and maybe this is the last layer, right? This is where predictions happen. So I don't want to get the predictions, because these predictions are for some other class, right? This is for the ImageNet class. It may not even be relevant for my data set like FashionMNet. So I don't want to look at this layer, but this layer, this is the last but one layer, or this layer, you can also use that. I can use this to get a feature vector. And this is what we call CNN code for this architecture. So just go through, feed forward all the way, but stop here. And this is, you can see, this is a 4096 dimensional vector. So that's why we were mentioning the 4096. Where is that coming from? It's coming from the architecture. The architecture has 4096 dimensional neurons, or hidden vector here. And this is where you extract it out and say, this is going to be my new starting point for my task. Let's say for my fashion MNIST data set, I'm going to start here, and I'm going to add in one layer or two layers or three layers of feed-forward neural network model, and then predict for the classes that I care about. Okay, so when you do this, what you obtain at this point is what we call a CNN code. So the activations at the last but one layer of an image obtained from a CNN arc. That's what we call a CNN code. It's a code because it is something that you may not be able to interpret. It's a code. It's a hidden feature vector with certain dimensions. So it's a code of a certain dimension. In this case, 4096 dimensional. So that's why you call it a code. It's coming out of CNN. So that's a CNN code, right? So essentially a feature vector that you can use for training. Okay. So let's look at some of the nuances. So we spoke about, transfer learning at a broader setting, but let's now kind of dive a little bit deeper and look at some of the nuances in transfer learning and the strategies that you can use in different contexts, right? So the first strategy is a CNN code plus a linear classifier. Okay, so I'm getting a 4096 dimensional CNN code, a feature vector. So I have an image, and then I have a CNN code. This is going to be my starting point. Add a linear classifier, super simple. Like, we've looked at logistic regression. Just do logistic regression on this 4096 dimensional feature vector and predict your, let's say for fashion MNIST, you have 10 classes, predict your 10 classes. Okay, so very simple. And this is something I would suggest trying out first for your mini project as well. Like, keep things simple, start simple, and see what you get. How's your accuracy? Okay, the second strategy is, so this is the same strategy, but you can use AlexNet, ResNet as your CNN arc. So the CNN net that you're using can be any of these, right? So you can have many other. You can try anything. Try anything that you like. There's lots of resources available on the web. So if you want to use the most latest one, ResNext. So there's also ResNext. There's like other random names that you find. You want to use some of those, feel free to try that out. And main thing is you're getting a CNN code. So you need to identify where are you going to cut off and identify the CNN code from that net, and then use that in your new model. Okay, so that's a very simple strategy for transfer learning. The second is freeze plus fine tune. So you freeze all but the FC layers. So this could be more than one layer of the net. So you can think of this also as obtaining a CNN code, but earlier than the last but one layer. Okay, so if you have, let's say you have these. Okay, so let's say this is your arc. So you can obtain a CNN code here. You can also obtain it here, or you can obtain it here. So this strategy is you obtain it at this point, and then you train from here. So you can think of it that way. Essentially, the second strategy is you shift where you're obtaining the CNN code. Is it the last but one layer, or you're moving it a little bit ahead of time. Um, and there is a reason to do this as well. As we discussed, the earlier layers are giving you, they're doing feature extraction, but the later layers are becoming task specific. So maybe your specific task, your data set that you're looking at is kind of different from the pre-trained model or what it was trained on. So maybe you don't want to use the last but one layer, but layer earlier because it's too task specific. So I don't want to stop there. I want to stop a little bit earlier, get a little bit more generic features that are not super task specific so that it can work for my task as well. If it's too task specific, then it's going to work for that kind of a task. It may not work for my task, my set of images, right? So I may want to go a little bit earlier. So that's essentially what the second strategy is. Shift the point where you're getting a CNN code and then train the rest. You can train, and even here, right, you can train the last layers of an existing architecture, or you can put in your own layers. Which has a different dimension as well. So if you're keeping in the layers as it is in a specific CNN architecture, we call that fine tuning, because you're essentially fine tuning an existing architecture. Or if you're adding in a new set of layers, then you're training those layers from scratch, right? So this is a second strategy that you can use for transfer learning. Okay. And then, yeah, you can do both. Let's say I have fine tune and also new layers. So I freeze some layers, I fine tune some layers, and I add my own layers, new layers. So that's like the complete kind of description for transfer learning. You can, if you want to have a full blown transfer learning model with all these components, you can do that as well. But for small data sets, this is overkill. You probably will be overfitting if you have all of these things. So for smaller data sets, you probably want to use the first strategy, right? Okay, so this brings us to the next question: when to pick what strategy, right? And what's the intuition behind picking these strategies for transfer learning for our data set and our task at hand? So a key insight on how to pick the strategy is to compare the new data set. So let's say your new data set is fashion MNIST, to the pre-trained model data set. So as we know, all of these pre-trained models are on ImageNet. So this 10K classes. So how does a new data set compare to the pre-trained model data set, right? In terms of size and similarity. So these are the two dimensions that you want to look at to, pick your strategy. So in terms of size, yeah, the new data set in let's say Fashion MNIST is much smaller than the ImageNet data set. Would you agree? Right? It doesn't have as many data points, maybe 60,000 data points, and your ImageNet has like 1 million data points. So size is definitely smaller. And similarity. So you had to also ask this question: is your Fashion MNIST data set similar, like the images that you're seeing there, the classes that you're seeing there? Is it similar to your ImageNet data set? Yeah. What do you think? Is it similar? Not similar? Yes, no. I haven't looked at all the classes in ImageNet. So, but sorry, Fashion MNIST. So I'm not entirely sure. But my guess is it's not very similar, right? It's going to be different. So based on these two dimensions, right, you can kind of have a thumb rule or devise a strategy for picking these strategies, right? So the first one is I have a smaller data set. My new data set is smaller, but it's similar to the pre-trained data set. So let's say I have a smaller version of ImageNet, and I want to make predictions on that. Then the suggestion is to use CNN codes plus linear classifier. So use CNN codes as it is, and then add a linear classifier there. And maybe you want to use CNN code from the last but one layer. The reason is it is similar to the pre-trained data set. So even though the last button layer is task specific, the task that you have, the new task that you have, is similar to the one you had before. So you can use the last button layer to extract the CNN code and add a linear classifier. Why? Because you have a small data set. I don't have bandwidth to train a like 3-4 layer FC, or I don't have bandwidth to fine tune my CNN model, CNN architecture, because I have a smaller data set. I might overfit, and so use this, okay, as a strategy. The second is you have a smaller data set, but it's different from a pre-trained data set. Okay, so it's a smaller data set, so I still want to, maybe use a simpler model. The parameters I have in my model want to be similar, so let's keep this, but use a CNN code from a couple of layers before. Why? Because I look different from my pre-trained data set. And as we know, the last but one layer is going to be more task specific for the task that the pre-trained model was trained on. And I have a different task or a different kind of a data set. So maybe go a little bit earlier and extract the CNN code from a little bit before. Okay, so maybe a last but two or last but three can give you the CNN code. Or you can extract the CNN code from the very end of the convolution module of the CNN architecture. Just before the FC layer start, that's where you get the CNN code, and then use that along with the linear classifier. Okay. The third, the third category that you might fall in is you actually have a large data set. So ImageNet has 1 million data points. Your new data set has 500K data points. It's kind of large as well. Okay, so now I have more options. I don't have to just use a simple model. I can do this freeze plus fine tune routine. I can freeze most of the layers, or I can, freeze the first few layers. I can also fine tune some of the convolution layers. So I have more options. The option 3 that we are looking at in the earlier slide, that would apply here because I have more data points to fine tune the layers of the CNN. And by doing this, I am able to get better performance, right? Because we know that a CNN architecture like Inception or ResNet or one of these more recent nets do work very well if on a very large data set. So why not fine tune them, then come up with our own architecture? So, but to fine tune, you need enough data points, and we do have that when you have a large data set. So depending on the size of the data set and the similarity of the data set to your pre-trained model, you can pick between these different transfer learning strategies. Okay. Any questions or thoughts so far? Okay. Cool. So let's do an in-class exercise. It should be straightforward, but kind of let's take a look at it. Okay, so hopefully you got a chance to look at the question. Yeah, so because the MNIST data set is, as we discussed, is significantly smaller than the ImageNet, you don't want to have a fancy model, especially with fine-tuning of the FC layers, fine-tuning of the CNN layers, but you still want to use transfer some of the information. So, but also because it's different, you may want to use a CNN code from a few layers earlier and add in a linear classifier on top of it, logistic regression. You can even add in a couple of feed-forward neural network layers as well if you want some nonlinearity on top of this. So this is a good option to go with. Okay. So yeah, so some pointers for mini project, right? So if you're using CNN codes plus linear classifier, there's kind of two ways to do this. is you can train with Pytorch. So essentially use the Pytorch model. Let's say I have ResNet. Load a ResNet model, freeze all the layers except the last layer, and then train it as a Pytorch model. So you're implementing it as a Pytorch model. Even though you can extract the code and train it separately, you can do it this way as well. Then you stay within the framework of Pytorch. And if you do want to go a little bit earlier, make changes, it's easier if you do it this way. Or if you're very sure, I just want to grab the CNN code and then I just want to use it somewhere else, get the CNN code, and then you can use logistic regression and scikit-learn or some other library, and then train and get the result. Can we think of other models for a mini project? Yeah, so as you might have guessed, you can obviously train your own model from scratch. Maybe I have a 3-layer CNN. This is your architecture. You can train that as well, but we don't know how it's going to perform, and it may require hyperparameter tuning and other things more than a transfer learning based model. But you can do that as well. So I want to use a 3-layer CNN. Let's say you came up with it, you can call it your name net. That's your net, you came up with it, but yeah, you'll see that you may have to do a lot of fine tuning, your account for overfitting and many other things. So I would definitely start from here, and then if you want to experiment on your own, you can also try that and see what you get. Okay, so there's a couple of transfer learning Pytorch tutorials that I've linked here. Do take a look, and we'll also go through one of them right now. Okay, so here we're looking at a Jupyter notebook that's actually publicly available. It's on transfer learning, and I've referenced this also in the slides. So we'll just kind of do a quick walkthrough. So there's a couple of things I wanted to point out here that'll be useful for the mini project that we have as well. So you see, usually any of these notebooks start with a lot of imports. So we're using Torch libraries, and so you're kind of going to load a lot of them. You see NumPy. Okay, NumPy is going to be useful for any vector arithmetic. You have to load these transform and models and data sets. These are again modules in Torch Vision. That's helpful. Matplotlib, useful for plotting. So if you want to plot things, then you have other libraries like time, OS, copy. Okay, but these are the main ones that if you're using Pytorch, you want to load all of these. You see LR scheduler, learning rate. So you have a learning rate for your stochastic gradient descent. You want to load that. CUDA NN. So you want to use GPU. So you have to load this. Optimizer. So all of these are straightforward. NN neural networks. Optim is optimizer. Okay, so great. And then there's some benchmark option that you can enable that can optimize for a particular architecture. Okay, so we do that, and then you load the data. So in loading the data, there's some things you can do, like you want to use normalization for train and validation. You can kind of normalize to the mean and standard deviation of images. So that's this. You can also, yeah, so random horizontal flip. So this is data augmentation. You see, you want to randomly flip it and still apply the same label. So you want to say, hey, whether I look at this way or that way, it's still the same image. So don't think of it as a different image. So that's simple, methods for data augmentation, right? Random resize crop. Okay, so we also do data augmentation here. This tutorial here is on the Hymenoptera dataset. So Hymenoptera are, I don't know if I'm spelling it right, pronouncing it right, but they are classes of insects, large insects. So this is an insects image data set, and you want to differentiate between different classes of images, insects. So Hymenoptera data. So this is a data set for that. You load it, and then you split it into train and validation. So there's that. And these are the classes. It's usually useful to have a data loader to load batches of data. So because if you look at stochastic gradient descent, it's using mini batch. So you have a batch size. So let's say you can have a batch size here, and you want to shuffle. So shuffle is true. So you keep things random. You don't want to. So let's say you have 1,000 data points and a batch size of 4. You're going through each batch of 4 data points. You don't want to go through it linearly. You want to shuffle it around. You want to keep things random. So shuffle equals true is doing that. And then number of workers, let's say you have GPU, how do you deal with that? Okay, and then you also have the device. CUDA 0 is, if you have a GPU available, then the default is CUDA 0. If you don't have GPU, then we'll use the CPU for training. Okay, all right. Visualize images. So this is useful to do for any data set. I would recommend doing it for fashion MNIST as well. Just see what are you dealing with. What kind of images are you looking at? Okay, this is taking some time, so I'm not going to. Yeah, all right. Okay, well, let's skip this. Okay, so let's look at the images from this data set, Hymenoptera. So you can see there's ants, there's bees. It doesn't have to be a single ant, it could be like a cluster of things. These are images that you would like to look at, right? I'm just kidding. But there's ants, bees, yeah, lots of different kinds of ants. Okay, great. And you want to be able to predict. Look at this one on the bottom left. It's not so obvious. You have to look a little bit carefully to see that there's an ant in there, but you still want to classify it as an ant, right? So data visualization, and then obtaining CNN code. So something that we spoke about in the lecture is, so how do we do this? Okay, so the nice thing about Pytorch is you can just say, I want to use ResNet 18 or ResNet 50 or one of these popular architectures, and they're pre-trained. So that's true. It's pre-trained model that I'm using. And now the key thing is freezing or not freezing. So for every parameter in my convolution layer, in my model, I want to require gradient equals false. So this is a parameter in Pytorch. You also see it in Keras or other deep learning frameworks that you want to specify if a parameter requires a gradient. Why? Well, gradient is what is getting updated so that you can optimize a parameter. If a gradient doesn't exist or you're not requiring a gradient for a parameter, it's not going to be optimized. It's not going to be touched. In other words, you're freezing those parameters if you say parameter dot require grad equals false. Okay, so if you say it's true, it's going to train those parameters, right? You're going to retrain all of those parameters. You have 4 million parameters, all of them are going to. So this just one switch here is going to determine whether you're going to retrain all the parameters or you're going to retrain a few of these parameters or freeze all of them. Okay, so here we're freezing all of the earlier layers. So you freeze everything. Essentially, you're getting a CNN code, right? This is equivalent to getting a CNN code from all the earlier layers. But you still want to fit a new layer for your class. So that's where this comes in. So in this case, I guess there's only 2 classes. It's ants or bees, right? So that's why the newly constructed layer is going from number of features to 2, because 2 is the number of classes. I want to predict 2 classes. In your fashion MNIST, you'll set this to 10 because you have 10 classes. Okay, and the number of features is the number of features coming from the last but one layer. So that could be 4096 or it could be whatever, depends on the architecture that you are using. So you want to capture that and specify this appropriately. So you do want to know what the number of features are. So you want to look at your architecture and say, okay, how many features? So you want to specify that feature here. And it's a nn.linear, so it's a linear layer. It's a last layer can be linear. And you can add yeah, so last layer is linear, and then you have softmax. So that's good. That's the equivalent to logistic regression if you do a softmax. So we're doing a cross entropy loss. We spoke about cross entropy a few lectures earlier. So this is what you would use for binary classification. So that makes sense here. And you also want to specify the optimizer. So use SGD with a certain learning rate. Maybe you want to use some momentum. So we haven't discussed these, what momentum means. We discussed learning rate, but these are some hyperparameters of the optimizer itself. The engine behind optimizing a loss function is obviously SGD, but it has hyperparameters like momentum and things like that. Okay, so I want to use that. You can use other optimizers, this Adam. You can experiment with those as well. And then there's a decay schedule. So this is your LR scheduler. The learning rate that I'm using, so maybe I start at 0.001, but usually people diminish it because you may not be making, you may start to converge as you go, but you don't want to decay it too quickly because then you will not make progress. So here, for instance, the author decided to decay it every 7 epochs. So every 7 passes through the data, you decrease the LR by a factor of 10, right? So multiply by 0.1. Okay, so that's a LR scheduler. So we did some settings for learning rate. We did some settings for the optimizer. You can change it to Adam, for instance. Let's try optim dot. Yeah, so you can see here, add a delta, add a grad, add a max. There's many optimizers. Okay, so we'll definitely try experiment with some of them. May not make a big difference, but again, helps you understand the nuances of training a pre-train or doing transfer learning in this case, right? Okay, so this is basically the setup. Okay, and then you can also try with true here. Okay, set this to true and see what happens. You know, how does your performance degrade or change? Are you overfitting and things like that? So those are things you can experiment with. All right, so that takes some time, so I'm not going to execute that. But once you set that up, you basically set up your hyperparameters, and you know you've defined your setting for your transfer learning, right? Now it's time to also set up how you're going to do the model training. So this is a module for that. A lot of this is actually happening from scratch here. So let's see if you want to take a look at this. It's not too complicated to look at this code, right? So if you look at this for loop, you're going through every epoch, right? And at every epoch, you have a train and validation phase. You want to track training error, you want to track validation error, and then you iterate over the data. So you get inputs labels from a data loader, and you are, let's see, backward. So this backward thing is actually doing the back propagation. Loss dot backward. This is like back propagation and computing gradients, right? And then taking this is gradient descent. So very simple. Gradient descent, as we spoke about, this is like the heart of training, right? This is where all the training happens. This is where you're learning from the data. So this optimizer.step is take a step in the direction of the gradient that you just computed using backpropagation and update your parameters to the next set of parameters, and then keep iterating through this. You keep iterating through this until you converge. And that's how we see that profile where the loss function starts to go down, the error starts to go down, and then starts to converge. That's after many, many iterations. Okay. And then you're keeping track of some statistics as well. What's the loss look like? So that you can actually graph it. Let's say you see all these graphs, that's, you have to keep track of the how the loss is looking like as you train. And then you have a loss for the whole epoch. So you do some averaging to compute this is basically the epoch loss, epoch accuracy. You can track the accuracy across every epoch. So typically people, when you look at the graphs, it's like the x-axis is the number of epochs, 20 epochs, 25 epochs, and the y-axis is the accuracy or the loss. So all of that is getting tracked here in the statistics. And then you iterate until you're done. So that's basically the train module, module here. And this is transfer learning right here. So before we've defined the parameters that go in for the transfer learning model, and now here we are actually training the model. We pass in the model underscore con. This is the hyperparameters that we set for the transfer learning, the criterion, the optimizer, the LR scheduler, the number of epochs, and pass it in the train module that we just defined here, and then train. Okay, so it's going to go through 1 epoch, 2 epochs, so on, blah, blah, blah. I kind of stopped it early, 4 epochs. And then you, at the end of each epoch, you can see what the train loss looks like and the validation loss looks like. So even here, you can see the training loss is going down, 0.58, 0.44. Well, actually, it's going up. All right, so it can fluctuate. So we know this is stochastic gradient descent, so it can go up and down. So that can happen. And then also we're tracking the accuracy. So the accuracy is actually also fluctuating quite a bit. So again, these are things that you may want to experiment with. So all of these hyperparameters matter, right? These things matter. The batch size matters. The learning rate matters. You just change any of them even a little bit, you'll get a different result. So if you do the training and you're like, oh my God, I'm getting a really bad accuracy, it turns out some of these hyperparameters, you might have picked it conservatively or incorrectly. So you may have to work on them. But these do provide a good starting point. So this notebook, for instance, gives you a good starting point. So you can start from here and then fine tune it as needed for the fashion MNIST dataset. Okay. And then, okay, so then you want to visualize your predictions. Okay, here's an image. Looks like let's kind of zoom in. Sorry. All right. Okay, so wow. So the first one, that's pretty good. Even to me, it's not clear what's going on here, but it looks like a bee. It makes sense because you're seeing flowers, so most likely that's a bee. So maybe the model's using the feature of seeing a flower and then making a prediction that it must be a bee because I see a flower. And then the second one predicted ants. So, okay. And then this one is pretty interesting again. Lots of bees, but the model is able to capture it. Not very clear that it's bees, but can capture it. Okay, so this is what I'm seeing from my prediction. So looks like the model is doing a good job at predicting the right things. Okay, so this is from the visualization standpoint, but you also have your accuracy metrics to tell you how good you're actually doing. Okay, so sorry. Okay, so that's a notebook on transfer learning. It's available. You can look at the link I've shared, and then there's other notebooks also available. But when you look at any of these notebooks, really ask what each of these components are doing. Like you can just use it as it is, but if you really want to understand, just ask questions of every single component of this notebook and to understand what's going on. Yeah. All right. I want to show you one more thing before we stop for today. Okay. Here's another notebook. Would also link this pretty useful for transfer learning Pytorch. And they actually experiment with all the things that we spoke about. There is, so let's say you want to use AlexNet. You load the model, so this model loading, pre-train is true, you load the model. If pre-train is not true, then your parameters would not be optimal. So you would have to train it from scratch. So pre-train is true gives you the optimal parameters. You don't have to, you can, you don't have to train from scratch. You can use the existing parameters and fine tune. So that's pre-train equals true. So you can see loading itself takes a lot of time. It's 230 MB. Okay, I get the model. So this is what the model looks like, right? There's con layer, relu, max pool, con rail, relu, max pool, con relu, max pool. So 5 of those layers, and then you have the classifier. So the first part, as we spoke about, this part is generic, and this part is specific to the task because it has a classifier. Even here, you have a 3-layer classifier. You have 1 layer here, 1 layer here, and then the last layer to make the predictions. Okay, so you can say it's a 3-layer neural net that's being used for classification here. So retrain, we haven't. So the default is to have required gradient for every single parameter. So we didn't set it to false. So this is retrain. Okay, you retrained on your data set, and this is what the loss function looks like. So we spoke about keeping track of the loss function. The x-axis is epochs, the y-axis is the train and validation error. You can see there is some gap. This gap does indicate overfitting because the train error is going down, but the validation error is not. So retraining all the parameters can lead to overfitting, and that's what we see here. There is more of a gap between validation error and train error. The validation is not going down after a while. Okay. What about accuracies? The train accuracy obviously is going to be high, and you can see it's getting close to 1, but that's not the real picture because there's overfitting. So when you go to validation, you see the accuracy actually drops. So that indicates there is overfitting going on, and retraining all parameters from scratch may not be the best strategy for this data set. But you still get a good, reasonable validation accuracy. So here you see 0.87, not bad, but not great either, right? Okay, so now let's do the CNN code that we spoke about, where we freeze all the layers and extract the features. So here, yeah, so by default, requires grad is true, right? So this is printing if requires grad is true or false. If I didn't do anything, if I didn't set it to false, it's true by default. So it's training all the parameters, both the feature layers and also the classifier layers, the convolution layers and the FC layers. So now we'll set it to false, okay? And this is one of the transfer learning strategies. Freeze all the layers except the last layer. So this is the last layer training. So you're getting the CNN code from the last layer, last but one layer, and then training the last layer, just using one linear model. So we add a linear classifier, a logistic regression. So this is essentially logistic regression, and then retrain. So just train the last layer. And you can see the validation error has gone up. So it was below 0.9 validation accuracy. Now it's more than 0.9. So even though I only trained the last layer, I froze everything else, I'm getting a better accuracy than training all the parameters from scratch. And this makes a lot of sense. So whatever we spoke about, we're seeing that happen here. Okay. And then fine tuning. Okay, so this is the intermediate. This is the third kind of strategy that we spoke about. You freeze a few layers and then you fine tune the rest. So here you can specify how many layers you want to freeze. The first 6 layers, the first 5 layers, and then I want to fine tune the rest of the CNN. And so you can see these layers. So here we're looking at AlexNet, right? So 1, 2, 3, 4, 5. So the first 3 layers are frozen. The last 2 layers are getting fine-tuned. Okay. Okay, again, go through the training, blah, blah, blah. And then let's look at the accuracy. Okay, so the accuracy is better than if you train all the parameters, but it's actually worse than if you just trained the last layer. Okay, so again, this is why does this make sense? Whatever we spoke about earlier. So look at the size of the new data set, compare it to the old data set. If it's a smaller data set, then just train the last layer, use the CNN code from the last but one layer, and that would be a good strategy to use. Yeah. There's other things in this notebook that's useful as well. And you can, replace AlexNet with VGGNet, Inception, ResNet, ResNext, blah, blah, blah. So just pick whichever you want to use and see what result you get. So this, I would say this notebook is even better than the one that we saw earlier. So maybe use this as a starting point for Fashion MNIST and just play around with it, understand, and actually I would say try all the strategies that we spoke about for transfer learning and see for yourself which is giving you a better validation and test accuracy, and why, and if it makes sense. So that will solidify your understanding of transfer learning for the data set that we're looking at. Okay. Any thoughts or questions on this notebook or transfer learning? Okay, so pretty useful. And the good thing about transfer learning is not just for CNNs. Let's say you want to train a natural language processing model. You want to enter into natural language processing. You want to deal with language. Guess what? You can do pre-training, transfer learning, all of the same things that we discussed here transfers to other domains as well. It's a very useful paradigm for machine learning, for transferring your learnings from one domain to the other. Okay. I think there's one more in-class exercise, so we'll do that and then we'll be done for today. Let's take a look at this. So yeah, I see people have shared. So it seems like 2 should be the right answer. The only thing is when your data set size is small, you cannot, fine tune a lot of parameters. So learning a big network from scratch is going to be difficult. So it is a use case for transfer learning. But when your data set size is large and your distribution is very different from any of the pre-trained models, you have enough data to retrain the model from scratch because your distribution is very different and transfer learning may not give you much gains. So when you have less data, you do want to transfer, learning because you can, you don't overfit and you cannot train a lot of parameters anyway. But when you have a large data set, that's when you have the flexibility to actually retrain all the parameters from scratch. Does that make sense? So it's a question of overfitting, and it's also a question of learning in this case. So transfer learning is useful when you also don't have enough data. So you don't have enough data, so you do want to transfer some learning from some other domain so that it makes it easier for you to learn. So smaller data sets do benefit from transfer learning. But with larger data sets, you may not see much gains depending on how different the distribution is. Okay. All right, so in the next lecture, we'll look at object detection, methods for object detection, image and instance segmentation. So we'll be moving from image classification into object detection. But in some sense, we have laid the foundation for any of the upcoming topics that we're going to cover in the next few lectures, because you extensively looked at CNN architectures, which is kind of the bread and butter of most of the computer vision, deep learning and computer vision models, right? So we kind of set the foundation for it. It's going to be easier for us to now go through other applications in computer vision. And then it may be a fine tuning of these networks that apply for these other applications, right? So you might still be using a CNN architecture, but with this kind of a bell and whistle or this kind of a modification, add in something else because you have a natural language processing. Let's say you have image captioning. Well, I have to have a captioning model, so that's going to come from natural language processing. Maybe use a LSTM or transformer. So add that to a CNN. So we're going to have these kind of additions as we go through the next few lectures. So yeah, I think the object detection is coming up next. We'll stop here for today, and if you have any questions or thoughts, feel free to stay back.